Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and this short video is going to consider, I suppose, the logic behind the binomial distribution formula. Yeah, the binomial distribution formula. Okay, so let's just write down that particular formula here. The formula says that the probability of something happening, okay, is equal to NCR, okay, or NCX, yeah, times p to the power of x times 1 minus p to the power of n minus x. Okay, it's a binomial experiment, so only one of two possible things can happen. It's either successful or it's unsuccessful, yes or no, so on and so forth. Okay, but with respect to this particular formula, there's a number of parameters that are important for us and that we need to know. The parameter n, n typically signifies or symbolizes the number of objects, in the experiment. Okay, p typically symbolizes the probability of some particular event, the probability of success or the probability of failure. So the probability of success or failure. Okay, and don't forget we have n objects, and x represents, I suppose, don't forget this probability of success or failure is with respect to one of the particular n objects. So x represents, I suppose, how many objects out of the n we're interested in this particular, I suppose, condition applying to. Out of the n objects, x represents how many of them are successful or how many of them have failed. Yeah, so x is the number, okay, the number of events, let's say, yeah, okay, or the number of, let's say, objects, yeah, okay, that, okay, have the particular condition, and what I mean by that is that are either successful or failure. Okay. Now let's try to just, I know the form looks a little bit complicated, okay, but for example, let's just look at an example. Yeah, for example, okay, if I have, let's say, 7 machines, okay, 7 machines, and the probability, okay, okay, of a machine needing repair, let's say, is 0.4. Okay, so you have a 40% likelihood that any particular machine will need repair on a particular day. Okay, so we have 7 machines, and the probability of a machine needing repair is 0.4. Okay, and what I'm interested in is what is the probability, okay, that 3 of the 7 machines, okay, 7 machines will require repairing. Okay, so just to run this particular example, okay, the important thing for us is to identify our 3 parameters. Well, n represents the total number of objects that we have, so in this situation here, n must be equal to 7. Okay, p is the probability of something happening. Well, the probability of any particular machine needing repair is 0.4, so p is equal to 0.4. Okay? And x is, I suppose, out of the 7 objects, or the 7 machines, or out of the n machines, it's the number of machines that have this particular condition. So in this case here, x is equal to 3, because what we're interested in, what's the probability that 3 of the 7 machines will require repairing, the condition being require repairing. Okay, so in this particular case, all we do is we fill in our details. So what we have is this, is the probability. Now, capital X in this case represents the experiment. Okay, so what is the probability, okay, that on any particular day, okay, that 3 machines, okay, will require repairing? Well, what we know that's equal to is it's equal to NCX. Let's fill in the parameters. So it's 7 C3, because x is 3, n is 7. P is 0.4, so it's times 0.4 raised to the power of x, in this case x is 3, times 1 minus 0.4 raised to the power of n minus x, which is 7 minus 3. Okay. When we do this out, okay, on the calculator, actually maybe what we'll do first is we'll just do the simple arithmetic. We'll do the subtractions, and then we'll do the actual calculation. So this becomes 7c3 times 0.4 raised to the power of 3 times, well, 1 minus 0.4 is 0.6. 7 minus 3 is 4. Okay. So from a calculator perspective, to calculate on my calculator here, to calculate the number of ways or the number of combinations, or the number of ways that we can select x objects from n, which is a combinations formula, from my calculator here, the NCR button is above the 5. So I want to calculate 7c3, so I'm going to put in 7, shift the NCR button, 3, and that gives us a value of 35. So there's 35 different ways that 3 machines could break down out of the 7. So this gives us 35. We need to multiply that by 0.4 raised to the power of 3. So we're going to multiply that by 0.4 raised to the power of 3. Okay? And we're going to multiply that by 0.6, okay? By 0.6 raised to the power of 4. Okay? So when I raise that to the power of 4, that gives me 0.29 approximately. Okay? So what I know is this, is that although the probability of one particular machine needing repairing is 0.4, or there's a 40% likelihood, okay? If I have 7 machines, the probability that any of the 7 machines, that any 3 of the 7 machines would need repairing is actually 0.29. Okay? And that's the way this binomial distribution formula works. But I suppose this particular video is trying to get us to a situation where we understand the logic behind this formula. Okay, and why this formula has this particular form. So what we really need to do is we need to consider the logic behind the binomial distribution formula. Okay, I suppose there's 3 important, let's say, there's 3 important formulas that we need to recall. Okay, and let me just put down the first general situation. Yeah, okay, if P is the probability, okay, of an event happening, okay, well then 1 minus p is the probability of the of the event not happening. Okay, that's important for us. Okay. That's our first important identity, okay? That if you're given the probability of an event happening, that 1 minus p is the probability of the event not happening. Also, what we're going to require in this particular journey, okay, is we're going to require the addition rule, okay? The addition rule. And in particular, we're going to require the mutually exclusive version of it. So that particular rule says that the probability of A or B is simply equal to the sum of the individual probabilities, so it's equal to the probability of A plus the probability of B. When events A and B are mutually exclusive of each other, which basically means that they can't happen together. For example, if I roll a 6-sided die, I can get an even number or I can get an odd number. If I'm interested in them probabilities, well then A being even numbers and B being odd numbers, those 2 events are mutually exclusive. If I randomly select a card from a deck of cards, I'm interested in getting a spade or getting a club, well, spades and clubs are mutually exclusive, so this version of the rule would apply. So when they're mutually exclusive, the probability of A or B happening is simply equal to the sum of the individual probabilities. Okay, and the next rule that we require is what's known as the multiplication rule. Okay. And in particular, we're going to use the version. Let me actually just put up here. This is for mutually exclusive events. Okay. And the version of the multiplication rule we're going to rely on is when the events are independent of each other. Okay. So what we're going to assume is, let's say in the machine scenario, is that each machine is creating the same type of widget or product. It's not the case that the first machine's output is passed into the second machine, which is passed into the third machine, and so on. Okay? So there's no dependence. They are independent of each other. And what the multiplication rule says is that the probability of A and B occurring is simply equal to the product of the individual probabilities. So it's equal to the probability of A times the probability of B when they are independent. So these three particular, I suppose, rules we're going to